As always, our recordings of our virtual meetups will be available on YouTube about a week after the meetup, and we'll post a message on Meetup when the recording is ready. So next, I am very pleased to introduce our speaker today, Michael McCourt. Michael McCourt was a Chicago resident for many years, first doing undergrad at the Illinois Institute of Technology, and later some time as a postdoc at Argonne National Labs. In between, he finished his PhD in applied math at Cornell, and now he works on SIGOPT from within Intel as a senior principal engineer. Take it away, Michael.
Thank you very much, Rebecca, for the introduction. And let me just say again that I am very, 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 very excited to be here. And in particular, very excited to be here as a member of Intel, which is indeed a sponsor of NumFocus. And I definitely want to thank everyone at NumFocus for helping sponsor this and other projects which really help build the computational community, which is very exciting, very, very exciting. I'm very excited to be a part of it and to see it continue to evolve over time. I have some slides here that I'd like to share. And in order to do that, I think what I'm going to try and do is share my whole window. And now if I do slideshow, hopefully, does that work, Rebecca? Does everything look wonderful?
Yeah,
outstanding.
We see
Very
just
good.
the slide. We don't see your notes or anything.
That's perfect. I have no notes. I'm not a notes guy. I'm just going to go for it. We're going to have some fun today. I've got some slides. I've got some Jupyter notebooks I'd like to run through and hopefully have a little fun with this today. Please feel free to ask questions as we go. Rebecca will stop me. I'd rather we make sure to answer questions, or if there are some really crazy questions, we can save those for the end. Let's kick it off. As you can see here, the title of the talk is Bayesian optimization and related sample efficient methods, which is a sort of a vague title in some ways. Obviously, Bayesian optimization, that's a very specific thing. Related methods, a very vague thing. We're going to dive through some of the foundations here and then stretch beyond what might normally be talked about and think about why some of these related topics are important and exciting. We'll see how the time goes here. Rebecca, if you could stop me sort of with about 10 minutes to go so that I know and so that everything's in my mind and we're pushing along. Fantastic. Thank you. All right. So first off, again, thank you for the opportunity to present. And thank you to the organizers, So Chung, Rebecca, Sherry, also Sherry. I don't think we've been introduced yet, but I know you're behind the scenes making some of this happen, so thank you. And So Chung invited me to give this talk, and we've been friends for a long time. So I'm really excited to be able to do this as part of, again, staying a little bit close to the Chicago community. Also, a quick shout out to the QMC Pi project, which So Chung and I think maybe Alexi is also here. I have spent a great deal of time working on. Very proud of that project and of all the great work everybody's been doing on it. So shout out to that. Personal introduction here, exactly as Rebecca had mentioned. Before 2015, I was what I would say I was an academic, doing just applied math or computational statistics, depending on how you think about it. A little bit of time in New York, but really a lot of time in Chicago as an undergrad, and also for doing some of the research that I did for my PhD was at Argonne. Some time out and about, some other places, postdoc at Denver. I was at Hong Kong Baptist University at various times over 2003 to 2015. And then in 2015, big change in my life, did the transition to the tech sector. I sold out. I became a corporate hack at that point. And I became in particular SIGOPT as the first employee in 2015 as a research engineer. And it just so happened that my research that I'd been focused on in Gaussian processes and kernel methods was really related to Bayesian optimization, which gave me the ability to contribute there. But I'll tell you what, since I left to do the tech thing, to do the industry life, I really love it. I really love the opportunities available to me, the cool projects I get to work on, the amazing people I get to meet, and the fact that I still get to do some exciting collaborations with academics, even though I'm no longer a member of that community. So it's been really exciting. We were acquired by Intel about, 18 months ago now. It's kind of crazy to think about that. And unfortunately, I don't get to do the fun stuff anymore. I don't get to do the actual writing of the code or the actual research so much anymore. I just manage, but I still really love doing it, which is why I took a chance as I was preparing this content to make sure that I did some of the actual coding again and actually got to put some stuff together. So quick outline of the session today, and I don't see my mouse, so I'm just gonna hope it's there. I can vaguely see it. Rebecca, can you see my mouse? Is it possible? Oh, I can see it now, maybe.
Yep.
Okay. All right. Very good. Very good. Thank you. First thing I want to do is motivate sample efficient methods. Then I want to talk about a very important tool in modeling called Gaussian processes. And Gaussian processes are really, really, really powerful. They're exciting in all sorts of different contexts. In particular, they're exciting in this topic of sample efficient methods. And then we're going to talk about how somebody might do some of this stuff in Python. Same with Bayesian optimization, which again is a very powerful tool in this case that often uses Gaussian processes and how to do that in Python. And then I'm going to talk about some of these other methods that I have listed here, which are among this related sample efficient methods topic, show a little bit of that in Python. And then I'm going to show some use of SIGOPT to evoke some of these methods. And in particular, we'll talk some about what SIGOPT is, how it's designed, and how it gives people access to all of these things without them having to know all of the crazy math sometimes that's behind the scenes. There is a GitHub here, and I'm sorry, Rebecca, I should have shared this before so that we could have posted it before. I will share it now in the hope that, oh, you know what, I'll share it at the end. I'll share the link at the end, but there it is if people want it. So I promise I will give it to Rebecca afterwards, or I'll give it at the end of the talk. All right. So let me start by talking about non-sample efficient methods. And in general, when you think about most machine learning methods, those are not sample efficient methods. In general, ML tools today are as powerful as they are and as capable as they are because they have a great ability to digest massive amounts of data. The most powerful tools are the ones that can effectively digest massive piles of data for the purposes of learning really complicated things, such as, gee, as I'm driving my autonomous vehicle, is that a car in front of me or is that a person? Is the car speeding up or is it slowing down? These are extremely complicated problems that require massive amount of data. And here I put two graphs in particular. The one on the right is a common one I often think about, which is showing sort of the size of some of these neural networks as represented by the size of these circles. 155 million non-zeros. This is a very old graph. I mean, nowadays they have even much, much, much bigger neural networks. But back when this came out, I remember thinking to myself, like, boy, 155 million weights in your neural network is a crazy number of weights. It's hard to even think about that. And yet these are the standard tools that people are using. And the way that you can learn things that have 155 million non-zeros, 155 million weights that you're using to try and learn complicated things, the only way you can do that is with a massive amount of data. So these are these, I'd say, sort of standard ML methods. And in contrast, sample efficient methods are methods which either seek to make do with a very small amount of data, or, and this is the main topic we're going to talk about today, they try to acquire exactly the right pieces of data in order to accomplish some goal. So instead of having maybe 1 billion rows in your data set that you're trying to study, maybe you have 1,000 or 100. And some of what we're really going to be talking about today is on the order of 100 or less samples and trying to accomplish things where you're going to be taking 100 or less samples. And then the question becomes, okay, what can be done in that setting? And in turn, how do we do it? I'm just setting a timer for myself so I don't forget how much longer we have to go. Let's push on here and talk about what these sample efficient methods are. The names of these Bayesian optimization, active learning, active search, active differential inference, Bayesian cubature. And in reality, the presence of the words Bayesian and active, these could all be titled Bayesian active optimization, Bayesian active learning, Bayesian active search. And in reality, that's because they all have a sort of very similar structure. And for those of you familiar with the topic, sequential decision making, really all of these topics are part of this sequential decision making framework. So the main point that I'm really emphasizing by talking about this is that our goal when we develop these tools or think about these tools is often to use Bayesian modeling or inference to actively drive whatever the desired iterative process is. And often it's a learning process. We're trying to learn about the optimum, or we're trying to learn about satisfactory outcomes that we search for. We're trying to learn what world we're living in through differential inference. We're trying to learn an integral through cubature, unsurprisingly. So the question then becomes, okay, I understand the goal. What is this? What is this framework that we're talking about here? What are we trying to accomplish? And while I'm saying the term Bayesian often, while I'm using fancy terms about machine learning, I want to emphasize that these topics have been thought about prior to posing them in a Bayesian framework. I haven't put links here, but I put links at the end of this topic to really emphasize the idea that while it is very common to pose these in a Bayesian framework, the reason for that is not fundamental. The reasons are because it provides convenient setup for the problem, a logical mechanism for saying, hey, here's a model, here's how I incorporate data into that model. And that allows you to make intelligent decisions. In addition to that, and this is probably the most important point, the second one there, it can incorporate problem-dependent or expert information to help improve outcomes, which again is very, very, very important when we're trying to be sample efficient. If I can enforce my prior beliefs about the world and greatly reduce the amount of data required in order to build models, I'm doing a good job. I'm happy about that. So if, for instance, I can impose information such as the pressure of something must be positive because that's just a physical property, or if I'm in Kelvin, then the temperature must be positive. If I can impose that, that can help me maybe build models more effectively, more efficiently. It also can help with theoretical analysis, but to be perfectly frank, I think most people who do Bayesian optimization only pay a lip service to theoretical analysis. It doesn't mean it's irrelevant, but a lot of the proofs aren't terribly practical in many circumstances for a lot of reasons that we won't get in here today, though if somebody would like to know, I'm happy to talk about them later. The one thing I want to emphasize is that for this session, and even honestly, to execute on some of these topics, you don't need to be an expert at Bayesian modeling and inference. It helps. But I wouldn't consider myself an expert at Bayesian modeling and inference. But I could still work on these topics because they can be posed from a variety of different frameworks. So don't feel scared when you see these words, a lot of fancy words here, Bayesian active, whatever, cubature, whatever. Yeah, don't worry. We're going to push through it. We're going to see a few things. And hopefully you guys are going to get the feel of the topic and why it's exciting. And if you want to dive deeper, I'm always happy to talk about that. All right. So this is the core structure underlying this sort of Bayesian optimization thing, but then more broadly, sequential decision making. Generally, these methods start with some sort of an initialization phase. Do they have to? No, but you might as well write it there because you could always say initialization phase is null, and that is fine. So in general, we talk about there being an initialization phase. We also talk about a conclusion phase. And it may be something as simple as saying, and now I'm done, or it may be some additional post hoc analysis of whatever took place during your sequential decision-making process. But the main thing, the main sort of rounded rectangle that you see here is this sequential decision-making iteration, this loop that goes on. Whereas with whatever data I have, I build some sort of model. Using that model, I identify what piece of information would make me the happiest in whatever I'm trying to achieve. And we'll talk about that in a minute. But there's some way to talk about the next best piece of information. Then I acquire that piece of information. Then I build a new model, identify the next best piece of information, acquire that piece of information. And this iteration here is this sequential decision-making loop that's underlying all of these Bayesian active methods that's going on here. Now, in reality, things can get crazy complicated. I'm talking about here as being sequential, but in reality, it can happen in parallel. It can happen asynchronously in parallel. In addition to that, this topic of identify optimal next piece of data, incredibly complicated. I mean, whole, millions of hours of research get poured into this question of even just understanding what the word optimal means. What does the word optimal mean in different circumstances? I might even argue that's a huge part of my job. It's just helping customers understand what they mean when they say, well, I want it to be better. I want it to be the best. So in reality, keeping this loop in mind and keeping in mind that we start by building some sort of model. We ask ourselves, how can we use this model to advance our interests? And then we advance our interests. That is the main thing that we're going to be talking about today. So before I get into this topic of the full iteration, I want to spend a chunk of time talking about this key thing that we were just mentioning here, building the model. What is it to build a model? And in turn, why do I have the word Gaussian processes on this slide? And indeed, Gaussian processes are a popular tool for modeling. They are not the only tool for modeling. Obviously, all of us are out there building gradient boosted trees, neural networks, or maybe even just good old fashioned linear regression. And those are also all models that one can build of things. Those are all very useful models. In particular, the three of those are all very useful models for situations where I have massive amounts of data. But if you were going to try and build a neural network on 5 pieces of data, I don't know, maybe you can. It's possible. I'm not going to tell you you can't do it, but I'll tell you what I think the right tool is for these really, really small data models. And I believe in my heart they are Gaussian processes. What is a Gaussian process? I'm going to say what the definition is, and then we're not going to think about it anymore. The definition of a Gaussian process is a stochastic process where point evaluations of the process have a jointly multivariate normal distribution with a defined mean, prior mean, and prior covariance. In reality, what does that mean? Well, we're just going to think about it based on the pictures we see at the bottom here. In each of these pictures, I've got the same 5 data points. The yellow circles represent function values. The orange bars represent uncertainty associated with those values. As you see here, a Gaussian process model is a model that tries to pass through all of these points, and in general actually will pass through all of these points, subject to how much uncertainty you have in your data. That does not mean that all Gaussian process models look the same. They can look like this over here, or they could be much tighter in trying to fit the data, which is maybe this model I have to the right here. Or they could be a little bit looser, like we have the model here. Or they could actually have no smooth derivatives, which is what this graph that you see down here is, this sort of crazy looking Brownian bridge style graph. Gaussian processes can have a lot of different things happen, but the reason they're nice is that they work in arbitrary dimensions. I don't recommend fitting a 50,000 dimension Gaussian process, but they kind of work the same whether you're in 2 or 20 dimensions, all the way up to maybe 200. You get past 100 too much, it's, in my opinion. Others may disagree. They do require prior beliefs about the desired model. And the impact of those prior beliefs is the different models that you see listed here. Each of these different models has different prior beliefs about the covariance. And when you think about covariance, when I think about covariance, and in particular this topic of a covariance kernel for Gaussian processes, when I say covariance, what I mean is, how does data that I've seen tell me about data I haven't seen? And different choices about the relationship between observed and unobserved data will yield different models that I fit. And in particular here, what I'm saying is, boy, the data that I've observed tells me very little about the points that I haven't observed, which is why I have this crazy stuff going on in between the observations that I've seen. And in contrast over here, what I'm saying is somehow, well, the covariance that I want is to yield the simplest model possible, something that does as little as possible. And so that's why it sort of has these very specific small bands, very little action between the points. And in fact, I know that this particular model that you're looking at here has even a stronger statement than that. It actually says it must tag this point on the left and this point on the right. It has required values that it's trying to achieve, as opposed to these other ones. This one has no required values. This one has no required values. This one is required to take the value 0. This one is required to take, I think it was the values 1 and 2 or something like that. So you can have all these cool behaviors with Gaussian processes. You don't need crazier things than that necessarily. We're going to spend a minute now. We're going to pop into a notebook to take a very brief look at Gaussian processes. In particular, we're going to look at this Franke function, classic function from, in my mind, approximation theory. And we're going to talk about this Gaussian process posterior mean and posterior variance. And when I use the term posterior, again, I know this sounds fancy, crazy, Bayesian, whatever. Don't worry about it. It's just, okay, I fit points that I've sampled at these locations to data observed from this function. And my estimate of what's going to happen looks kind of like this, which again looks kind of like the function. This here is a statement of the variance, and that's basically an estimate of my uncertainty. How sure am I about the model that I built? Where you see that it's red, that means I'm not very sure. Where you see that it's deep blue, you mean I'm feeling okay about it. And unsurprisingly here, I've got a whole lot of uncertainty and my model's pretty wrong about that. So that's not surprising, right? All right, let's pop into our notebook now. And I see some chat. Did people have questions? I'm sorry. Oh, no, she's already sent. Very good. Very good. Thank you very much. Thank you very, very much. Very good. So here we are. We're going to pop into one of the notebooks that is available in that repo that I put together for this. And as you can see, it's just some content for playing with Gaussian process, nothing crazy. And you'll notice I've imported just the bare minimum packages, in my opinion, bare minimum. I don't know, maybe you could write this whole thing yourself just from base Python, but please don't do that. Use the wonderful num focused sponsored packages, NumPy and SciPy to do this kind of work. Also Matplotlib to visualize the work, or Seaborn or Plotly or whatever you love, it's fine. I've put here some math, but honestly, I've just put it as a placeholder. Don't worry about the math too much. All right, we're not going to worry about the math. I am going to say that the Gaussian process that I've created here does have some fundamental assumptions going along with it to just simplify the code. All right. And what I really wanted to show is that even though Gaussian process is a little scary, I'm talking about joint multivariate, normal, posterior distribution, blah, blah, blah. This is it. This is the whole thing that's required. And you can see all this is just storing the data. Nothing else to it. Very, very, very small. You do a little Cholesky factorization of a covariance matrix that you compute. The covariance matrix is nothing more than just these lines. Very, very, very simple covariance matrix. You'll notice here, this is the exponential of r squared. That should sound like a Gaussian in your mind. That is the Gaussian covariance kernel. Other covariance kernels exist as well. It's also called squared exponential covariance kernel. And you know, computing the mean, look how simple that is. Very, very simple. It's just a simple matrix vector product. I know it looks simple. I also know, having done this for a long time, that there's some crazy stuff behind the scenes there. Why does all this stuff look like it does? Why does all of it happen? That's a whole other topic. But I just want to show you that it doesn't have to be scary. Things can go bad when you're doing Gaussian processes. I wouldn't pretend that they can't. But in general, things don't have to be crazy. Here, I've just created a very simple function. This is this Franke function that we were looking at a second ago. And I've created some points on which to plot the Franke function, do a little contour plot. And now we're going to take some points randomly scattered throughout the domain, doesn't matter where they are, and see how it looks relative to the function. And you guys can see here that that's really all I'm doing. Process variance, length scales, observation noise. You're asking yourselves, what are these things? These are the so-called hyperparameters of a Gaussian process. There can be other hyperparameters as well. In this particular case, I have simply fixed these hyperparameters a little bit below. We'll talk about how these can be learned, but in reality, we don't have to learn them. We can just fit them or just choose them. I don't recommend that in all circumstances, but for a simple example here, it's fine. And in reality, we can just compute the mean and variance just using this very simple computation we have up here. Nothing crazy. Very, 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 very straightforward. But in reality, are you going to do this on your own? Yeah, you can. And if you're going to do research on the topic, you absolutely are. But in reality, other people have already done this stuff and you don't need to be doing it. So I've put here some examples using the GPy and BowTorch libraries on how to do exactly the stuff that I just did above. So if you want to follow this, you can do this with these nice, wonderful open source libraries. I'm a huge fan of BowTorch. Outstanding people. It's based on PyTorch, which was developed at Cornell, and some really great people at Facebook, now called Meta, have worked to develop BowTorch, and it's really a fantastic tool, and I absolutely love it. So if you see it's very, very similar. It's not exactly the same. The reason it's not the same is because they're right here. They're fitting those hyperparameters that I just picked personally above. They're actually fitting them. So they're making different decisions. This is not the same Gaussian process, but you see it's very similar. And you can see here that I also have done, oh, not GPy, I'm sorry, sklearn. I don't know why I put GPy. I did sklearn because sklearn is a num focus thing, not GPy. So I'm sorry. Later on, I'll add a GPy example as to how to do it. But sklearn example on how to use the same Gaussian process regression concept. So you can feel free to execute this on your own. If you dare me, I would rerun the kernel, but I want to save some time for some other stuff. So I don't want to rerun this notebook. It's not a big deal. It's nothing crazy in here. So that is how I think about, there we go, slideshow. That is how I think about the very, very, very basics of Gaussian processes. Like I said, it can be a really cool, expansive topic, or you can keep it really tight if you want it to be. And we're going to be able to actually get through Bayesian optimization without going any deeper into Gaussian processes than that. Now, you may see terms like RBF interpolation, Kriging, ridge regression discussed in literature, feel that these are all similar to Gaussian processes. You are right. They are. They absolutely are. Very, very, very similar. They're not the same, but they are similar. I am more than happy to talk about this, but it's just well beyond what we can talk about right now. So happy to talk about it later on or another time. So what is Bayesian optimization? And I hinted at this idea that sequential decision-making has this model, next step, model, next step, model, next step structure. Here's what that looks like. I have a model of the data I've seen thus far. Now I need to choose a next point. And I'm using sort of vague terms here, improvement, expected improvement. We haven't defined those yet, but we'll get to it in a second. I'm going to maximize whatever I think of as the best thing I can do. And then I'm going to sample at that point. And when I sample at that point, that is this new point that I've observed here. Based on this new point, I fit a new model. That new model kind of tells me, gee, Mike, I think you should really sample over here. I would choose to sample at the next point. That's going to give me something going on over here. And then I move on and I move on and I do it again and again and again and again. And this iteration right here, this is the key to Bayesian optimization. Fit a model, next point. Fit a model, next point. So how do we get this next point? And the answer is this phrase acquisition functions. Acquisition function is a strategy for defining the utility of a future sample given the current sample. And in general, acquisition functions balance exploitation with exploration. Exploration is the idea of I want to learn about what's going on with the function. I need to know everything about it. Exploitation is the idea that I only really need to know a very specific piece of information to accomplish what I'm trying to accomplish right now. And what I'm trying to accomplish for Bayesian optimization is I'm trying to find the maximum. If there's a region of the function that's full of terrible values, I don't really need to be spending much time searching there. That's the idea of exploitation. And this balance between these two is what drives the sequential decision-making process. Now, as you can see here, we've got 5 different acquisition functions. So there are a lot of acquisition functions. There are actually, I mean, more than I can count. People are coming up with new ones every day, new ones that maximize some slightly different balance of exploration, exploitation, or leverage some slightly specific information that only exists in one domain or another. But the point is, different acquisition functions will tell you to search different places, sometimes only a little bit different. Sometimes if you have this black acquisition function here all the way to the side, maybe you want to do that. So different things can happen based on how you choose to power your sequential decision-making process. And in particular, the relationship between the model that you choose and the acquisition function can even be complicated. Here again, I've got 3 different models all fit to, in this case, I sort of did a little bit more crazy data. It's the same data, but higher variance. So if I chose higher variance in my model, perhaps, and you can see different points that I might want to sample based on each of these outcomes, because each of these has different models. So the model can have a big impact on things. In addition to that, the acquisition function can have a big impact on things. That can mean that the choice of these things can be scary. I'm not going to lie. Let's go through a little bit of Bayesian optimization in Python right now. And in particular, take a look at the idea that, hey, I've got my function that I'm trying to study, but of course I can only sample it at a very small number of points. In particular, let's say these 1, 2, 3, 4, 5 points so far. I'm going to use these 1, 2, 3, 4, 5 points to ask, where is the next best place to sample? And that's going to be a function of the model that I fit, which is sort of roughly represented here. You see, it's not a very great model yet, but it might be eventually. And I'm going to use that to power my optimization process. So let's pop back into our notebooks right now. And in particular, I've got the same very basic stuff again. Nothing real crazy doing here. You don't need the crazy stuff just to get the ball rolling. Same object I've imported here. I added a couple extra things that I need for the Bayesian optimization. And now I've defined a quantity called expected improvement. Expected improvement is the classic powerhouse of Bayesian optimization. You do not need to use expected improvement. There are a lot of different options, but expected improvement has powered more experiments than I could count in the world. Everyone starts with expected improvement. And there's a reason for that. It works. It's not any more complicated than that. Expected improvement is really powerful. Does that mean that it's the best for all situations? Not even close. Does that mean that it's even better than some standard tools that exist in other circumstances? No, I think there are other things that are even better. I think knowledge gradient is probably better. There's a variant of expected improvement called noisy expected improvement that I think is probably better in most circumstances. But those are often much more computationally expensive to execute and also significantly more complicated to understand and implement. Whereas expected improvement is literally just right here. That's it. That's the whole thing. Super duper tiny. I take the posterior of my Gaussian process, the posterior mean, I take the posterior variance, I compute a little extra, just z-score, sort of, because of course we're talking about normal random variables here. Take a z-score. And then this is it. That's the whole thing. It's so easy. And that's why people love it. It's just so easy to look at. It's so easy to debug. The gradient of it, I didn't do gradient optimization here, but if you do gradients of it, the gradient's not even any more complicated than this. You have to throw in the gradient of the variance and the mean, obviously, but it's really, really, really simple. And that's why people love it. And that's why it's so popular. And we're about to see right now that even though it's really simple, it still works. It just kind of works. So here I've again chosen some hyperparameters for my Gaussian process. Again, you could choose these any way you want, or you could fit them at each step, and we'll show that down below. And I've evaluated the expected improvement all over the domain for plotting purposes. And then what I've done in order to find the max expected improvement in each step is literally I've just evaluated a bunch of random points. Took a bunch of random points, whichever one had the highest expected improvement, that's what I took, which is totally reasonable to do because I have a small dimensional space and because expected improvement is very easy to vectorize. In general, you should definitely do something much smarter than this. You should do some sort of gradient-based optimization method, probably prefaced by some amount of differential evolution or maybe CMAES if you have a pure continuous domain. If you are looking for a tool to use to do gradient-free optimization, I absolutely would say Nevergrad. Again, it's a Facebook tool. Nevergrad is an amazing tool. Definitely use that. And I also would say to do gradient-based optimization, honestly, anything you do, even just basic atom is fine. It'll work fine in my opinion, in my experience, it usually works fine. And here you can see the process of the iteration. I'm going to expand this out and show you step by step here. 5 points. This was the next point we wanted. Now I've sampled at that point that appears down here. I fit a new model. It doesn't look all that different from the other model, ironically. So now, okay, but the expected improvement at that point has dropped considerably because I've already sampled there. So now I'm saying, okay, I should sample here. I sample there. Ooh, hey, my model's getting a little more interesting. Now, expected improvement says to sample there. I sample there. Okay, hey, a little bit more interesting. I keep going through this process. Wherever is the highest expected improvement, I sample. And I go on and on and on like that. Here it said try and sample here. Not because it necessarily thought it was a great value, but because it thought that it had a very high variance. If it has a variance, it has a high chance for improvement, which means a high potential expected improvement there. But it turns out it was kind of bad. It samples here, maybe samples there. Okay, all right, I'm sampling. And as you can see, as we go along here, the samples do tend to be sort of clustered around the good points, but scattered out there as needed based on, again, what the model hyperparameters are. And as you can see, when you look at this model, this is not a great model of this function, right? But what it is a good model around the optimum. And that is how Bayesian optimization and all these sample efficient methods work. They do not need to produce good models. When you are sampling, when you are trying to be sample efficient, you do not need good models. What you need is the right data. And if you use even a bad model in the right way, in this case through expected improvement, it can still power your optimization process. Now in 2D, you could use a good model and still find the optimum, because it doesn't matter, because 2D is very easy to talk about. But if we're talking about 10, 11, 12 dimensions here, and you want to get the optimum in 100 points, you need to very quickly throw away bad parts of the domain and not try and build models in bad parts of the domain. And that is the power of Bayesian optimization, and in particular, Bayesian optimization using expected improvement. Below, I show quick examples of how to do this with BowTorch. Now here I've gone through and done, and you know what? I'm even going to add this note here. If you are not interested in doing the BO yourself, but just want to have something run it for you, use Facebook's Axe. So I put the link to Axe in the other notebook, the Gaussian process notebook. Axe is the tool that Facebook uses to simplify the interface. If you actually want to do the BO yourself, power it yourself, this is how you do it. You'd run this loop, you import all these BO things, and in particular, you fit your GPyTorch model at each step along the way, and you evaluate expected improvement using their expected improvement acquisition function. So they have a separate one which takes in the Gaussian process and other information that is required. But it's the same loop as it was before. I fit my model, which I fit up here, or fit it down here. I create my expected improvement evaluation tool, and then I optimize it. Above, I optimize it by taking a bunch of random points. They optimize it much more intelligently than that. And you can see it's the exact same process, and you end up with the same scattering of points right near the thing there. I also show the same thing for scikit optimize. It's a little harder to extract piecewise information out from scikit optimize. So I just show the final outcome here, which is called very easily right here. I show the same thing with Optuna. Again, a really cool tool out of the people from Preferred Networks that prints out a lot of information that happens. And then they run the same thing. They get you your good values. I know we're running up a little bit against the clock here. I see that it's 1:45 already, and I'd like to be done about 10 minutes from now. So I am going to pop back over to the top and say that there are these other sequential decision-making topics: model building, viable outcomes, integration, model parameterization. And in particular, I have here a notebook that creates this GIF for us, and I'll open up to the slideshow right now to show this GIF, to show that active learning, optimization, and search all are similar in that they are all iterative, but they're trying to accomplish very different goals. Active learning is literally trying to poke around the domain in some way that the points are spaced out well enough to learn about the function we're trying to study. Optimization is trying to just find the optimum, which is why we're kind of end up targeting this main region over here. Active search, on the other hand, is trying to find suitably high values. In this case, I just defined suitably high as above a threshold, 0.8, I think. And you see, it's just kind of jamming points all up in this region. Once it finds a happy region, that's what search does. It jams things up in that region. The notebook, in order to follow this along, is available up there, but I am not going to run that right now. I am going to go right to using SIGOPT because that's what I want to do for my last 10 minutes, because I am from SIGOPT. I think SIGOPT is an amazing tool. And the reason I think SIGOPT is an amazing tool is that because while I think that everything I've shown thus far is cool, in reality, Bayesian optimization could do so many more amazing things. Mixed parameters. I'm talking categorical, integer, continuous, and maybe conditional parameters in there if you want. Constraints. I'm talking metric constraints and parameter constraints. Multi-objective optimization. Parallelism. Failures. I know I wrote the word failures there. I guess I deleted it. All the stuff you want to be able to do with Bayesian optimization. You can do that. You absolutely can do that. The literature is out there if you want to read it. But SIGOPT has been designed to box all that stuff up and host the computational elements of this for you on our platform in order to allow you to do your sequential optimization and search process without having to think about things. SIGOPT was founded in 2015, acquired by Intel in 2020, and is free to use for everyone in the public right now, thanks to the generosity of Intel. I say here it's on a limited account. It's a pretty generous account. And if you need more, you call me and we'll work it out. In addition to that, it has expanded use of all the cool functionality for academics. Again, if you need more, talk to me. Let's work it out. I want to get you stuff to make cool stuff happen, because that is what I am most interested in. SIGOPT works exactly the way that we're talking about here. It is this sequential decision-making loop. I have left this up because I told you guys I am a corporate sellout. I have to put this slide in one slide of every talk I give. But in reality, yes, SIGOPT is a really cool tool. You tell us what kind of problem you're interested in solving. We give you configurations to test. You test those configurations. Here, this is obviously specifically talking about tuning a machine learning model. Let's say things like your learning rate, your dropout, your momentum parameters. We can help you tune that. We tell you what to do. You tell us how it performed. And this loop is this sequential decision-making loop. SIGOPT functionality is meant to be very abstract. So you don't have to concern yourself with any of this Gaussian processes, Bayesian optimization stuff at all. All right. We hide all of that from you. In order to get started on SIGOPT, and these slides will be available to you, so you'll be able to follow this up. Sign up for free right now. Grab an API token. You are going to need your API token. In general, we tell people to run SIGOPT config. I'm going to run through a notebook where you actually can avoid doing that, but in general, running SIGOPT config is definitely the right thing to do. In SIGOPT, every optimization, the word we use for optimization is experiment. Function evaluations are called runs, though runs also encapsulate other meta information about the function evaluation. Parameters are suggested by SIGOPT, so those are your X values, as we saw before, X1, X2. And metrics are reported back to SIGOPT, those are your Y values. And here now we're going to pop over to our SIGOPT demo here. And you see here, I'm doing some standard, very basic imports. This one I actually am going to run. What the heck? I hope it works. We'll see. So we're going to do standard stuff. This are the standard set of SIGOPT config actions you would use. I'm not going to use that now. I'm going to use the other one. Doesn't matter again. In general, it is a super bad thing to do to put your SIGOPT API token right here in your code. So don't do that. Don't worry. I'm going to roll this token as soon as this topic is over, but I made sure to give myself a token that, fingers crossed, will actually work. In general, what you should do is you should store this as an environment variable, and then you won't need any of this at all. SIGOPT will just pick it up from your environment, so that way you don't share it with other people accidentally. Here's a function evaluation. This is the exact same function we were studying before. I've tossed in that threshold we were using before, as I mentioned, for that search problem, 0.85. Here we go. SIGOPT create experiment. This is how you tell SIGOPT what problem you're trying to solve. And in particular, I have the exact problem we were talking about before. I'll pull it up again. From 0 to 1 in 2 dimensions. That is the problem I'm trying to solve right here. I need to tell SIGOP that. I need to tell SIGOP what metric I'm trying to optimize. In this case, metric is just Y. It doesn't have to be a fancy name. You can make it a fancy name, and we will in a second, but it just has to be a name. I don't care what it is. Tell it if you want to maximize or minimize. And in this case, optimize. Of course, you're trying to optimize it, although we'll talk about other options in a second. I gave us a budget of 25 iterations, and we're going to see how well we can do in 25 iterations. Here I've created the experiment, view it on the dashboard. Let's pull that up right now. I have to punch in my password. Of course I do. Please don't steal my password, internet. All right. I hope I know my password now that I think about it. There we go. All right. Very good. So here is the experiment that I have just created right now. And all of you, of course, can do the same thing, probably with a different, as I mentioned, token. Frankie function, you can watch this experiment progress, and I'm about to click the button to do that. But before I do that, I'll rewind for a second and show that inside SIGOPT, you pull open your API tokens by clicking here. You also can see all the various orgs and teams that you're a part of. You don't have that button, site admin, because you people are not site admins. And you can check the various projects and experiments that you're a part of here. Here you can see some experiments that I ran earlier to confirm that all of these things that I've written up actually worked correctly. But you could see these experiments, and in particular, you could share these with other members of your team, or even externally. You have the ability to share an experiment with anybody in the world, even without giving them access to your account, which I like. So we're going to watch this execute. I'm going to go down here and I'm going to run a loop where I ask SIGOPT for a next set of parameters to test. What is the next thing I should run? And I just noticed that my headset just died for some reason, not sure why. Hopefully all of you can still hear me. I think you can. And in addition to that, we are going to report back to SIGOPT run.log metric. And that run.log metric is going to tell SIGOPT how this turned out. I'm going to start this up right now. And there we can see that as things are running, we are going to be able to view it on the dashboard. I've added here this statement time.sleep2. In reality, you wouldn't do this. I'm doing this just to simulate what something actually looks like so that we can pop over here and actually monitor things as it's going along. And there we can see as things are going along, we can watch how long various runs are taking. Of course, they're all going to take roughly the same amount of time here. And this is the progress of the experiment so far as we creep along 1, 2, 3, 4, 5. This will update every 30 seconds, I think. And you will see this graph continue to update. And you also have the ability to click into the analysis page, and there's a more updated version of this graph, and survey some of the information that's available, in particular for this example that's 2D. You can see the sampling of the points and unsurprisingly, the clustering of the points around where the optimum is there. And I am going to pop back over to the summary. And we can see here we're 18 deep out of 25. Things are progressing. In reality, though, I know what the answer is for this particular problem. It is like 1.219. I have the ability to click on the best observation, and it'll pull me up to a page that is specific to that run. So if I just want to share this information with other people, I have the ability to do so. Click back over here, and you can see we are done, 25 out of 25. It says no failures up here, no failed observations, unsurprising because we didn't allow ourselves to report any failures. I'm just gonna very quickly here confirm, just want to confirm that we can still hear me, even though my headset just died. If something happens, write a note to me so that I can hear it. And that's how you run SIGOPT. And you'll notice here, there's actually no Bayesian optimization. It all gets run on SIGOPT side. It all gets organized on SIGOPT side. And you do not need to care about those things. And in addition to that, I have the ability to pull the data and plot the outcome. And this, of course, looks very, very, very similar to what we were seeing a second ago as we saw the points scattered around. But SIGOPT is doing all the smart stuff around, as I mentioned before, fitting the Gaussian process. I'll run one more type of experiment now. We mentioned before this idea of a search experiment where I'm going to set a threshold. Here I'm telling SIGOPT what that threshold is, and then I'm going to run this, and this is going to give me a different set of information. I'll let that run, and while that's running, I'll pop back to a completed version of this, which I hope is this. I think it is. And we can see here that, in fact, these points end up being a good deal more spread out than they were for the pure optimization problem. And we also see some of these points grayed out in this particular situation. The reason they're grayed out is because they don't satisfy the threshold. We set a threshold for ourselves of 0.85, and our goal was to find a bunch of points higher than 0.85 that are somehow spread out throughout the domain. And that's what we ended up doing. And if we click into the currently running experiment, hopefully we see that it's doing exactly that. Well, it just so happened the first point happened to be a good point, but in general, they won't be. That's what we're seeing here. And again, we're having points spread out that are all high performing points, which can be really useful to learn about high performing regions of the domain. At this point, I will kill this. And I will mention, and I won't bother to run it because they'll take a second, but you can also run optimization or search on multiple metrics. You can run search on actually like 4 metrics, but in general, well, up to 6. But in general, if you're going to do optimization, which is to say multi-metric stuff, you should probably be doing that, in my opinion, on 2. And that you can actually do in a sample efficient fashion, which again, I'll pull up one of the completed experiments here to show what the impact of the Pareto frontier is. This Pareto frontier here is obviously only an estimated Pareto frontier, but it is a pretty good approximation to what's going on right now. And in particular, I see someone has a question. I will answer that in just a second. In particular, the problem we're solving here is a sort of fun problem that I like to consider often, which is, okay, I'm going to pretend I have the global max that I found from some previous experiment here. Given that I have the global max, how can I find points that are high performing, but are kind of far away from the global max? And that's a problem that can be solved sort of with this multi-metric concept here. And when I do that, the outcome looks like this, basically, which is, okay, I have my optimum, but I'm scattering points out around from the optimum because I'm trying to get away from the optimum. So that's this region right here where I'm at the optimum and I'm trying to walk away. And then as I get further away, I try and search this region a little bit more, this region a little bit more, and then I end up in this region. And these are the different parts of the Pareto frontier that we end up seeing observed here and that we can visualize here on SIGOPT. With that, I will wrap it. There's one other experiment that I sort of had to show here, which was a metric constraint style experiment. So suppose I'm requiring SIGOPT to only find answers outside of this circle. I have the ability to do so by saying, please don't search inside this circle, and reporting that to SIGOPT by saying, set the distance from the global max to be at least, in this case, 0.3. And that turns to be, okay, I find this answer instead. And then it finds that answer and it's happy. So with that, I am going to pop back to my slides and pop down to the bink references slides. Here's some good references on GPs. Questions. And I see a question. Rebecca, would you mind trying to talk right now so that I can hear you?
Sure. Do you hear me?
See, that is interesting. I cannot hear you right now. So I'm going to stop sharing my slides. I'm going to figure out why that is. I see why that is. Could you try talking now?
Yeah. Do you hear me?
Well, okay, maybe I don't understand how my computer works. That is fine. People type to me, I can talk and type. I'm going to answer this question and then I will wrap it. How does SIGOPT compare to Optuna? First off, Optuna is a really cool tool. I have a couple friends at Preferred Network who built Optuna, Shotaro Sano, and Hideaki Imamura, and also Masahiro Nomura, all of whom are really awesome people doing really amazing work. Optuna is a great tool, but it is powered by a different mechanism than SIGOPT is. Optuna is primarily, to this point, I think, almost exclusively powered by the tree of Parson estimators mechanism. And in particular, the TPE mechanism is great for quick scaling and fast iteration, so minimizing the amount of computation that's going on, which is really nice if you're taking care of the computation. If SIGOPT is taking care of the computation, it matters a little bit less. And in general, I think most people would probably agree. If somebody disagrees, but I'm happy to listen to it. But I think most people would probably agree that Gaussian processes are significantly more powerful. The Parson estimators mechanism. So I'm going to see if I'm able to fix this now. So that is why I think Optuna is a very easy to use tool. And like I said, I gave you the exact instructions on how to use it. I think it's a fantastic tool. I do think SIGOPT is going to be more powerful, especially in the multi-metric situations, especially in very sample efficient situations. Tree of Parson estimators mechanism, the tree element, was designed to scale to tens of thousands or hundreds of thousands of observations. But if you're only doing 40 observations, you're not getting the benefit from it, but you are paying the penalty of using a weaker modeling tool than a Gaussian process. But like I said, I still think Optuna is a really cool tool, and I definitely recommend checking it out. But I also definitely recommend checking SIGOPT out because we allow it to abstract out some of these advanced functionalities, including, for instance, metric constraints, which can be very difficult to implement, but that I think we handle very effectively. Rebecca, or yes, Sherry, absolutely happy to answer.
Yeah, I just put on the transcription.
I just don't know how my damn.
You can't hear us. Maybe you can see the words.
I don't know.
The transcription that I'm saying.
Oh, wait. Oh, now I can hear. Perfect. Very good.
Oh, great.
There we are. Very good. Yeah.
Okay. Yeah, anyone can feel free to unmute and ask your question or ask in the chat.
Apologies for taking so long there on the talk, but I'm really glad we got to cover all of that. And I promised the links. Here's the link. Sorry, or I think you already shared the link. Yeah, you shared the link. Let me share the link to the slides too. And I also will roll my token so that nobody creates a million experiments on my token. Hopefully that works. And I'm going to roll my token right now. Go. All right. Anything else? Anything else? No, that's not.
Okay, maybe we'll call it again. Thank you for such a engaging talk, Michael.
Perfect.
Yeah, just as a reminder, we usually have our PyData meetings on the 4th Thursday of the month. So stay tuned. We'll be posting on Meetup soon. Bye, everyone.
Take care, everyone. Thank you very much again.
Bye-bye.